Thank you to the organisers for giving me this opportunity to speak. It's always fun to say that when you organise your own conference. So I'm going to talk about yet another lithium problem, I guess the classic lithium problem, and also I guess bring together a couple of threads that we've had in this conference, which is we've been talking about accreted stars and all the exciting differences between accreted stars in the Milky Way and trying to see how they're different from stars in the Milky Way. And this is all about how, I'm trying to find my mouse to make that go away because I can't see how, I'll survive. I've got things on my screen that's covering up a bit of my screen and I can't find my mouse. But I'm going to talk about stars that are the same everywhere. And so this is the fact that when we look at accreted stars, they also show Spite Plateau and lithium. And so for those of you who will cover the basics of this, this is all about the cosmological lithium problem, and it's the idea that some dwarf stars don't have enough lithium. And this comes from that, in a very black box, hand wavy, cartoony kind of way, you measure things in the cosmic microwave background, and that tells you how much of certain elements formed in the Big Bang. So it tells you how much deuterium, how much helium-3, how much helium-4, and how much lithium-7 formed, and other elements, but these are the ones we're going to talk about here. And then we can go and measure the amounts of these elements in certain parts of the universe. And so you can go and make a measurement of how much deuterium. You can measure gas that you think formed you can measure gas that hasn't had a lot of processing to it, and you think is the representative of the primordial abundance, and you get a number that matches really well to the Big Bang nucleosynthesis prediction. You can go and do the same thing for helium-4, and you get a pretty good value. The problem is you do it for lithium, and there's this huge offset. And this is the cosmological lithium problem. And where we do this, and so the reason that lithium is this interesting element because we can measure it in stars. It's the only one of these primordial elements, these Big Bang elements, that we can measure in stars. And so where we do it is in these middle poor dwarf stars in the halo of our galaxy. And this was noted by Spite and Spite back in 1982. They went and measured all these halo stars. And what they found was that for a large range of metallicities, they all basically have the same lithium abundance. And the reason that these stars are interesting, the sort of model is that these stars have these stars don't have large convective zones. They're not doing a lot of mixing. They're maintaining or retaining the lithium abundance they were born with. And so if you've taken a really old star and it forms from old gas, it should have the lithium abundance of the old gas. And if you look far enough back in age or metallicity or redshift or whatever, then the metallicity, the lithium abundance should be primordial abundance. And at the time of Spite and Spite, their sort of understanding of this was that this was the primordial abundance. And then, unfortunately, then we went and got cosmic microwave observations and other predictions that showed that there was this big difference between the Spite and Spite values, the Spite Plateau here, and the Big Bang Nucleosynthesis value with the blue line. And lots of observations have taken place after this. And you can go and throw GALAH onto this. And so this is what GALAH looks like. And the Spite Plateau just sticks around. So the red dots are all of these warm dwarf halo stars. The colorful background is the rest of the dwarf stars in GALAH. You can see all sorts of exciting, interesting structure going on. Like there's this, I can't see where my mouse is, but there's that sort of structure at high lithium and sort of up 2.9, and there's all sorts of interesting things that happen with lithium. But when you go and look at the middle poor part, they're all the same, unfortunately or fortunately. And so there's been lots of investigations so the red line. So there's been lots of investigations and models about how to explain this. You basically say, oh, the model is wrong, or that we don't understand nuclear reaction rates, or that the stars are actually doing something to their lithium, but the stars started a high lithium abundance and then they are reducing themselves down. There's actually something happening in the stars, the lithium abundance. And the one I wanted to investigate was that maybe there was something about the Milky Way. So this was actually inspired by some papers like Milero looked at this recently with GALAH DR3. And so I was sort of inspired by this to look at it more generally with GALAH, that maybe there's something about the Milky Way. And sort of oops, there isn't an extra bit there. But this sort of is taking the idea of that you could change the amount of lithium in a galaxy because it's formed in novae, or it's formed, there's whatever is producing the lithium or depleting the lithium in a lower mass galactic system. You can change the overall lithium abundance more easily. Like the classic alpha need, where the alpha need happens in a galaxy depends on the mass of the galaxy. And could lithium be doing a similar thing? Now, the problem is that we want to look in dwarf stars. Dwarf stars are intrinsically not very luminous. You can't observe them in other galaxies very easily. So then we have Gaia-Enceladus comes along. And this is fantastic because now we have this large population of stars that we think formed in another galaxy. And the question is, what does the Spite Plateau look like for those stars? What does the Spite Plateau look like for accreted stars? Ones you can really be sure are accreted. And so I went and found the Gaia-Enceladus stars in GALAH DR3. So this is using Fourier's classification based on J phi and square root of JR. The Gaia-Enceladus stars stick out the top there. And then I also defined a couple of other populations, so a retrograde halo population and a prograde population and a disk. So there's going to be, as Sven was pointing out in his talk at the start of this conference, drawing boxes in parameter space is maybe, you're drawing a box and there's arbitrary lines and all sorts of things like this, and there's going to be some overlap and some contamination, but this is what we have. This is what I did. And so then you're like, well, what does the Spite Plateau look like for all those populations? And it's kind of like a whomp sound as you go, oh, they're all the same. We haven't found, well, it's exciting in the sense it's all the same and this is a result, but it's not exciting in the sense of discovering something groundbreaking and revolutionary. But what it shows is that no matter what of these dynamically selected populations you look at, the Spite Plateau is the same. So this tells us that there isn't anything obvious about the galactic formation environment that affects the lithium abundance of a dwarf star. Now, the one interesting thing that we did identify in this was these stars. So there's a handful of stars that are very they're on halo orbits, and they are not extremely hot in their sort of solar mass stars, and they have huge lithium abundances. And this is where I go, I have no idea what's going on with this. I think in the paper we do the classic, they could be binaries, because you invoke binaries when you don't know what's going on and these sorts of things. So they could be binaries, it could be some sort of binary mass transfer happening. If anyone has thoughts about what could be causing stars, random dwarf stars, to have huge amounts of lithium like that.
Minutes, Jeffrey.
Okay, I'm basically done, that's good. So we found these two things. So I guess in conclusion, the Milky Way is not special when it comes to lithium, and the Spite Plateau looks the same no matter what dynamic selection you want to make. And so basically it doesn't seem like it matters where a star came from in terms of it's a dwarf star in terms of its lithium abundance. Spite Plateau looks the same everywhere. But we do find this handful of lithium-rich dwarf stars. And so the question is, where have they come from? How have they become lithium-rich at their particular metallicity? So thank you.
Great, thanks, Jeffrey. Do we have questions online? Or hands raised? Oh, Paula has a hand up. Yeah.
Hey, just a question about the last point here. Could you elaborate a little bit more about any kind of systematics you can have in the data? I mean, there are a few. I assume that you checked them or to see if the abundances are real?
So we did look at the spectra, and the lithium line of those stars is substantially stronger than stars of the same temperatures and everything. Like, I don't have a plot to show, but you can draw a little box in temperature, gravity, metallicity space and go, what do all these stars look like? And they have exactly the same spectra apart from that lithium line. And those stars do have substantially stronger lithium lines. Some of them, at least one of them, you can see the error bars on some of them are pretty big. So some of them are a wee bit noisier, but the one that is in panel B, the really high lithium star, that is a really large, like you can see a really strong lithium line on that one. And it's a good signal spectra.
Do you want to follow up, Paula? Or...
No, cool.
Okay.
I didn't know about it. So I just learned that they existed. Okay.
Yeah, this regime is like this parameter regime is really hard. Like we've looked, Jeffrey, Sarah, we've all looked at a lot of these stars, and sometimes you see signatures of binarity in the spectrum, but sometimes it's just unfortunate that you don't. So it could be that these are binaries. That would be my personal bet. But yeah, Jeffrey is the person analyzing these. So these will be really interesting to follow up and maybe take a second spectrum or something like that. I'm not sure, Jeffrey, do we have plans to for example, do follow-up observations of these?
We should, I guess. I'm sort of like, I sit here with like 600,000 stars on my computer and go, do I need more data?
Yes.
Sometimes you do, yeah. That's well, the good thing is
you don't need more data of the same. You need just a specific more data of some things.
Yeah, we need different data. Always ask for different data. All right. Do we have another question? I don't see hands raised. So in that case, we're perfectly on time.